Hi everyone, welcome back to chemistry. In this video, we're going to talk about the relationship between temperature of a gas and pressure of a gas, which is shown with Gay-Lussac's law. We talked about pressure versus volume. We talked about the relationship between temperature and volume. So now we're going to figure out, hey, how are temperature and pressure related? So in Gay-Lussac's law, it says that the pressure exerted by a gas is directly related to the temperature of the gas. And remember, with gas laws, we're always talking about temperature in Kelvin. Okay, this is Gay-Lussac's law right here. Another equation for you. Again, this will be given to you on exams. So it says P1 over T1 is equal to P2 over T2. So if we look over on the right there, we've got our initial temperature at 200 Kelvin and our initial pressure at 1 atm, 1 atmosphere. And if we heat up the temperature to 400 degrees Kelvin, 400 Kelvin, not degrees Kelvin, our pressure is also going to double. So it goes from 200 Kelvin temperature to 400 Kelvin, and our pressure is going to go from 1 atm to 2 atm. So they are directly related. So just like Charles' law, this is a direct proportion. Okay, so instead of inverse. So as I heat that temperature up, as I raise the temperature on my gas sample, I'm also going to raise the pressure. Again, we've got to hold some stuff constant so that we can actually compare these two things. So in this case, we're going to hold volume and the amount of gas, or the number of moles, constant. Okay. All right. So a gas has a pressure of 645 torrs. So actually, I didn't talk about torrs much, but 1 torr is equal to, it's just another unit of how we measure pressure. So 1 torr is equal to 1 millimeter mercury. Okay. It's a 1-to-1 ratio. And then remember that 760 millimeters mercury is equal to 1 atm. Okay, again, given to you on an exam, these two. All right, so let's keep going. So a gas has a pressure of 645 torr at 128 degrees Celsius. What is the temperature in Celsius if the pressure increases to 824 torr, but volume and number of moles remain constant? All right, so spoiler alert, we're going to use Gay-Lussac's law. So Gay-Lussac's law says P1 over T1 equals P2 over T2. So let's see, we got to kind of do some labeling here. And I'm also noticing we got degrees Celsius. And even though I want to end up in Celsius, we got to switch to Kelvin first. So let's actually give ourselves a little more room here. I'm going to put this over here, and let's go ahead and convert to Kelvin first. So my temperature that I'm given was 128, so we know Kelvin equals degrees Celsius plus 273. So that's going to equal 128 plus 273, which is going to equal 401 Kelvin. All right, so let's do a little labeling here. So we got 401 Kelvin. That's going to be probably my T1, my initial temperature, right? And 645 torr, we'll call that my initial pressure, P1. What would have happened if I would have said those were both P2 and T2? Yeah, it actually wouldn't matter. So as long as you keep your P1 with your T1, right, your initial with your initial, and your final with your final, you could plug them into either side of those equations. But you can't split them up, right? You don't want to use your initial pressure and your final temperature, right? And you don't want to put those both on one side. But if you use your initial and your initial on one side and your final and final on the other, you could flip these around. It would be totally fine. So what is the temperature in Celsius if the pressure increases to 824 torr? So this would be my P2, right? That's a unit of pressure torrs. And then my temperature, T2, is what I'm looking for, my final temperature. Oh, and I forgot to look. Oh, I got it. All right, so let's go ahead and plug that in. So now I'm ready to use this equation, so we can bring it over here. So we'll go step 2. And let's go ahead and plug in our values first for this one. So we got, just to kind of vary things up. So we got a P1, which is 645 torr, divided by T1, which is 401 Kelvin, right? I got that from over here. And then we got equals, I don't like this line here. We got that equals P2, which is 824 torr, divided by our T2, which is our unknown. All right, so we want our T2 to be alone. So let's go ahead and get it alone. So you can cross multiply here if you want, or you can just work through it, you know, kind of the long way by multiplying by T2 on both sides, and then taking this number and getting it over to the other side by using the reciprocal. But let's go ahead and cross multiply. So we'll do T2 times 6, let's go back to red here, T2 times 645 torr equals 401K 401K times 824 torr. Got to get myself one of those. And then let's divide each side by 645 torr to get T2 alone. That's going to cancel out that 645 torr. We'll also do a quick unit check on this side. We've got torr on the top divided by torr on the bottom. So let's get rid of those torrs, and we're left with a temperature in Kelvin, which is great because we definitely want to be in units of temperature. We do need to convert back to Kelvin, but that's okay. We can do that. All right, so T2 equals 401 times 824 divided by 645. And that's going to equal 512 Kelvin. Sorry, I was just checking my sig figs there, so that looks good. So 512 Kelvin is our final temperature. But what does that equal in Celsius? So let's go ahead and convert back to Celsius. So again, K equals degrees Celsius plus 273. So K we have, which is 512, equals degrees Celsius plus 273. So we're going to subtract 273 from 5. All right, and that's 239 degrees Celsius. So that's my final answer. All right, so that's the final temperature if the pressure increases to 824 torr. So that's it for Gay-Lussac's law, but let's also go over the combined gas law. So the combined gas law is kind of cool because it brings together pressure, volume, and temperature relationships. All right, so the combined gas law uses pressure, volume, and temperature relationships that we learned from Boyle's law, Charles' law, and Gay-Lussac's law, where the number of moles, N, does not change. So we hold the moles constant, but we can write a combined gas law that takes into account all of these relationships that we've looked at. And that combined gas law is P1 times V1 over T1 equals P2 times V2 over T2. All right, so let's go ahead and see how this works. So again, let's just write that down here just so we have it in front of us. So P1 V1 over T1 equals P2 V2 over T2. All right, so that's our combined gas law. So a sample of helium gas has a volume of 0.180 liters. So let's go ahead and label these as we go. So 0.180 liters, let's call that V1, right? That's our initial volume for our helium gas sample. It also has a pressure, an initial pressure, P1, of 0.800 atm, and a temperature of 29 degrees Celsius. So that's going to be our T1. Notice how all of these are our initial volume, pressure, and temperature. I'm grouping them all together. I could have also called each one P2, V2, or T2. It doesn't matter as long as you kind of keep that group together. That's our initial pressure, temperature, and volume. Okay, then it says, at what temperature in degrees Celsius will helium have a volume of 90 mils and a pressure of 320 atm? So let's call this volume is going to be what? Yeah, V2, right? Volume, our final volume. That pressure is going to be our what? Yeah, P2, our final pressure. And we're looking for our final temperature. So looking for our T2. Okay, so we got a lot of variables here, but that's okay. We can do this. But let's kind of scoot over here so we have a little bit more room to work with. So let's go ahead and, as always, let's convert to Kelvin first. And we'll go 29 degrees Celsius plus 273 equals K. So 29 plus 273, 29 plus 273 is 302. So Kelvin equals 302 Kelvin. All right, so that's our, what is that? Our T1. So T1. All right, so let's go ahead and plug it into our equation. So we got P1V1 over T1 equals P2V2 over T2. And notice this is combined, right? So we've got our combined gas law here. We've got our V1 equals P2V2. That's just like Boyle's law, right? And then we've got our P1 over T1, P2 over T2. Okay, and then we've got our V1 over T1. Oops, I meant to highlight that. V1 over T1 and V2 over T2, okay? So all of those combined. All right, so let's go ahead and plug stuff in. So P1 is 0.800 atm. And then we got V1, which is 0.180 liters, all over T1, which is 302 Kelvin. That all equals, so that's my left side. And then on the right, I have P2, which is 3.20 atms. And then V2, which is 90.0 mils. Okay. Ooh, this is a great example. Okay, notice how we have one of our volumes in liters and one in milliliters. That's no good because eventually we want those units to cancel, and we can't cancel them as they are now. We can't compare apples to oranges. We need to have apples and apples, or oranges and oranges. So let's go ahead and convert, since I've already written the liters down, let's go ahead and convert mils to liters. So let's call that, let's just do that on the side over here. So I'm converting my V2, which is 90 mils. So 90 ml. Let's convert that to liters. So remember, 1,000 mils is 1 liter. Okay. So that's going to be 90 divided by 1,000, or you could also think of it as moving the decimal place over to the left 3 times. So that's going to give us 0.09, let's go 00 liters. just to have our 3 sig figs that we started with. All right, so we got 0.0900 liters. So now we can actually, we're actually going to be able to get rid of those liters there. Okay, so let's go ahead and plug that in back into our equation, 0.0900 liters. And then divide it by T2, which is our unknown, right? And let's move our converting step a little bit over here, just as a side note. All right. So we want to get T2 alone, so we can cross multiply. So let's do that. So we got T2 times everything on the left, top left, okay, and then we got 302K times 3.20 ATM times 0.0900 liters. Whew, all right. All right, so now let's get rid of all this junk that's next to our T2 by dividing. Cancel that stuff out. But we got to do the same thing to the other side. So 0.800 ATM, 0.180 liters, and I'll come back with that number in just a minute. All right, so that is 604 Kelvin. And let's just do a quick unit check. So, we got ATMs on the top and ATM on the bottom, atmospheres on the top and the bottom, so those cancel, the units. Okay, we got liters on the top and liters on the bottom, so we can cancel those out. And then we're left with Kelvin on the top, which is perfect because we wanted to end up in a temperature. Okay, we specifically want to end up in degrees Celsius, but that's okay, we can convert. But take a look at how I cancel these out and make sure that that makes sense. The units will get you. So 4 Kelvin. So let's go ahead and convert that to Celsius. So convert degrees Celsius. So T2, actually, let's get rid of that. Let's go K equals degrees Celsius plus 273. So 604 equals degrees Celsius plus 273. So 604 minus 273 is 331. And that should be our final answer. So that's the temperature the helium will have at a different volume and pressure than what we started with, using the combined gas law, which is right here. A lot of steps, but just try to keep organized with your units and your conversions and stuff like that. All right, so in chemistry, sometimes you'll hear the term STP, or standard temperature and pressure. And this is just something that scientists created in order to, or kind of agreed upon as standard values for temperature and pressure, in order to be able to compare things easier, to compare, make comparisons between gases. So if we hold everything at standard temperature and pressure, STP, we can kind of compare the volumes of different gases a little bit easier. So standard temperature and pressure means a standard temperature is 0 degrees Celsius or 273 Kelvin, okay? Oh, and a standard pressure is 1 ATM. Usually it's expressed, for standard pressure, it's usually expressed in ATMs, but remember that 1 ATM equals 760 millimeters mercury, so you sometimes will see this as well. I usually just like to think of STP as 273 Kelvin and 1 ATM. And that's just going to allow us to quickly make comparisons between different gases. Okay, standard temperature and pressure. So at standard temperature and pressure, it actually so happens that a mole of gas always occupies a volume of 22.4 liters. Doesn't matter what kind of gas you have. If you have a mole of any gas, we find that at standard temperature and pressure, right, 1 atm, 273 Kelvin, 1 mole of gas occupies a volume of 22.4 liters. Always, 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 if you're at standard temperature and pressure. Okay, so we call this its molar volume. Okay, so you can use that molar volume as a conversion factor. So 1 mole of gas always equals 22.4 liters at STP. Okay, if you raise the temperature, it's not going to be the same. Okay, remember, raising the temperature raises the volume of the gas, right? But at standard temperature and pressure, this is always true. Okay, 1 mole equals 22.4 liters of any gas. So we can use these as conversion factors, okay, where you have 1 mole of gas on top and 22.4 liters on the bottom, or vice versa. So pretty cool. This is really, really useful in chemistry. So you do need to memorize that. 1 mole of gas is 22.4 liters. 1 mole of gas is 22.4 liters. So this is how you can kind of relate the volume of a gas specifically. Okay, not a liquid, not a solid, gas specifically. The volume of a gas to the moles of a gas. All right, so let's try this out, because I think the best way to memorize it is to practice. So 1 mole of gas equals 22.4 liters of gas at STP. Okay, so what is the volume at STP of 4.00 grams of CH4? All right, we know how to get from grams to moles, right? We've been doing that. So let's do that. So 4 grams of CH4. We want to get to moles. So grams are going to go on the bottom. And 1 mole of CH4 goes on top. How do we figure out how much 1 mole of CH4 weighs? Molar mass, molar mass. So let's go ahead and calculate the molar mass. I'll see you back here. You know how to do that. So, all right, I cheated and just checked the slide below, which has the weight. So 16.05 grams of CH4 is in 1 mole of CH4. All right, so now we're in moles of CH4, which is great. But we want to get to liters. So let's cancel out our grams of CH4. What do we know connects moles of CH4 gas at STP to liters? Yeah, our handy dandy equality up here. Okay, so let's say we got 1 mole of our CH4 gas, methane. Okay, yeah, that's methane. 1 mole of methane at standard temperature and pressure is always going to be 22.4 liters of CH4. Okay, so we go from moles to volume. Kind of cool. All right, let's do this calculation and I'll meet you back here. 5.58 liters of CH4. Final answer. And it's an option, so that's always a good sign. All right, let's try the next one. So how many grams of helium are present in 8 liters of gas at STP, at standard temperature pressure? So 8 liters. So remember, we start with what we're given. So we know 8 liters. So let's start with that. So 8 liters, and it says of helium. So 8 liters of helium. Oh, I forgot my little multiplication signs. Sorry. So 8 liters of helium. So we know that 1 mole of helium has how many liters? Yep, 22.4 liters of helium. All right, so we can get rid of those liters. Now we're in moles. Is that what we want to end up in? No, we want to end up in grams. So what do we know that connects moles and grams? Molar mass. Okay, I'm going to cheat again and just look down here at what the molar mass is. So it's 4. So 1 mole of helium is 4 grams of helium. So we can cancel that out. Remember, that's on the periodic table. So I got 1.43 grams of helium. Again, it's one of the options for our multiple choice question, so that's always a great sign. All right, so that's it for this video. If you have any questions, as always, let me know, and I'll see you in the next one.